Alright, so now we're in part 2. And part 2, we are talking about the correlation coefficient. So there's a numerical way to help us quantify the amount of scatter in a scatter plot, and that is to calculate the correlation coefficient. The correlation coefficient. So this measures the strength of a linear relationship between two quantitative variables, input, output. So you will never actually have to calculate the correlation by hand, but you should have an idea of how it's calculated. So the correlation coefficient is denoted with R. It will always be a value between 1 and -1. Here are some examples of scatter plots with their correlation coefficient. So this is a scatter plot of X versus Y. Its correlation is 0.98. So on a scale from -1 to 1, and if you look at that on a number line, here's 0, here's -1, here's 1. This number's next to it like 0.99, 0.5, 0.25, -0.5, -0.99, you know. So you've got different values. They range from -1 up to a +1. There will be nothing bigger or smaller than 1 or +1. -1 means a perfectly straight line going down. So this means the dots are lined up perfectly straight. They make a perfectly straight line going down from left to right. +1, perfectly straight line going up from left to right. Perfect world. 0, horizontal line, straight across, no association. 1, as X increases, nothing happens to Y, there's no association. So anything in between, and then we talk about getting more scattered, farther away. So here, as you move closer to 0 in this direction, these points go from here to becoming more spread out and more spread out, but still going up from left to right. These get more spread out, but still going down from left to right. So this has a very high correlation, very tight to that line, not that spread out. These are more spread out, okay, not just scattered everywhere, not horizontal straight across, still going up, so the correlation is about 0.51. Okay, this has a correlation of about 0.1, slightly positive, but barely positive. It's almost like there's no association, horizontal lines going across. This would be a fairly strong negative correlation. And correlation, a strength of a linear association. So now, the way R is calculated, and you never have to do this by hand, well, if you take stats in college, you will have to calculate it by hand for a few times, unless you learn how to use technology, which they don't even teach you. You have to teach yourself. So you either learn to do it by hand, or you learn how to use technology. Okay, so consider the scatter plot for calories versus fat for beef products at McDonald's. So this is the same one we had on the other page. It says there seems to be a very strong association, so the correlation should be very close to +1. Okay, how does the relationship change if we standardize both variables? So this is just walking you through how we calculate R, which you don't have to do. But the idea, what they're going to do is they're going to take every X value and every Y value, and they're going to change them into Z-scores. Okay, so they're going to change every X value into its Z-score and every Y value into its Z-score. So you've got all these X values of fat. So if you look at the other page, that one's all written on, but if you look at this last page, like you would have had an ordered pair that's like just about 9, 250. And then this one would have been like 12, 300. So you'd have like 9, 250, 12, 300, and you'd have all those X values. So what you do to find the Z-score, remember, is X minus the mean of the X's divided by the standard deviation. The Z-score for the Y's will be every Y value minus the mean of the Y's by the standard deviation of the Y's. So the Z-score for the X's is only based on the X values. So it's like this is its own little data set here. So I keep my X's as like its own data set, because it could be a data set all by itself that we just look at all kinds of stuff that we did in the last chapters. So we could change each of these into the Z-score. So we take the mean away and we divide every one of them by the standard deviation. Okay, and then we do the same thing for the y's. We find the average and the standard deviation, and then we change each of these to the z-score. So that's just the formulas here. This is the mean of the x's, and this is the standard deviation of the x's. This is the mean of the y's, the average number of calories divided by the standard deviation in the calories. Average fat grams, standard deviation in fat grams. And so then what we're going to do is we're going to replot all of the z-scores. So these are the z-scores for the fat grams. And remember, z-scores are always between, well, there's 0 is the middle. The 0 is the mean of the z-score, and the standard deviation of the z-score or standardized score is 1. So all we've really done, we have the same picture, but now we just moved it, you know, we moved it so 0's right here, 0's in the middle. Okay, so now what we notice is that since it's positive, we notice it's in quadrants 1 and 3. If it were negative, it should be all in quadrants 2 and 4. And really what we need to do now on the next page is the rest of calculating those z-scores. Again, you don't have to do it by hand. So what we look at, since having a majority of the points in quadrants 1 and 3 indicates a positive association, we will use the products, the z-score of the x times the z-score of the y. So now we're just taking every x and every y value and multiplying them together. So they were always in quadrants 1 and 3, so they're both always like either positive, positive, or negative, negative. So we multiply those. So you're going to multiply every pair of z-scores, x and y, the ordered pairs, and then you're going to add them all up, okay? And if the sum is positive, you have a positive association. If you were in quadrants 2 and 4, so if you were like here and here, you'd have a negative and a positive and a positive and a negative. When you multiply, you'd add them all up and get a negative association. So you can have a positive or negative correlation. Okay, so if there's no association, the sum should be close to 0. There would have been, you know, like some negatives and some positives. So what we do then to find R, we have our products, every z-score, x and y multiplied, we add them up, and then we divide by n minus 1. And so for that, we got a z-score of 0.997. So when we use the word correlation in statistics, we're referring to the correlation coefficient. Okay, the correlation coefficient, this correlation, we're referring to R. R is the correlation coefficient. It describes the strength of the linear association only. Okay? If you want to describe the relationship in a more casual way, just say association. Correlation is only referring to the R value, the strength of the linear. R is sometimes called Pearson's correlation coefficient because Pearson was the one that first used it. So here are properties that you'll need to memorize. You need to utilize these. So for the value of R does not depend on the unit of measure. The value of R does not depend on the unit of measure. Because what we did with all the units is we changed them into z-scores. Z-scores have no units. Their label is number of standard deviations above or below the mean. So, for example, the relationship between height and weight is equally strong if we use inches and pounds or centimeters and kilograms. It doesn't matter. So, R has no units. R is called the correlation coefficient. It means the strength of the linear association. It doesn't have the same units as any part of any problem does. Okay, the value of R does not depend on which variable is x and which variable is y. You could switch them around because the products are the same regardless of which order you do them in to find the z-score. Okay, so R is between -1 and +1. When R is greater than 0, it's a positive. So from here on up, it's a positive. From here on down, it's a negative. As R gets closer to +1, the relationship is stronger and has less scatter. As R gets closer to 0, the relationship is weaker and has more scatter. So as you move on this scale, okay, as you move on the scale from -1 to 1, as you move in, that gets getting weaker. Moving in is getting weaker. Moving out is stronger. In is weaker. Okay. Out away from 0 is stronger, in is weaker. Okay, only positive and -1 when the data are in a perfect line. This is the only case where the values of one variable can be completely determined by the values of the other. Okay, The value of R is a measure of the strength of a linear relationship only. It measures how closely the data fall into a straight line. An R value near zero, however, does not imply that there is no relationship or only no linear relationship. For example, quadratic or sine, cosine data may have an R close to zero, even though there may be a strong relationship present. It's another shape. All right, so even though R only measures the strength of a linear relationship, it does not tell us if a linear relationship is appropriate. Okay, only a residual plot, which we won't even make today, only a residual plot can do that. The correlation coefficient just measures how much scatter there is from a line on a scale from -1 to 1. Whether or not it's appropriate to use the line, we don't know. Okay. So, this data here, take a look at this. This is definitely not linear association. This is definitely a curved association, but you can still calculate the R and you get a -0.95. So there's still a fairly strong negative association, even though that might not be the best scenario here. So a line is probably not appropriate, okay? This one, R is -0.52, not a very strong correlation, strong linear association, but this would be better for a linear association. It does definitely have a more linear form. All right, so please don't confuse correlation with cause and effect. And I've heard this on TV a lot of times, listening Sunday to football. They talk about correlation not being causation. So you have to think about the relationship. So here they're showing a graph. This I just think is a pretty funny graph. It talks about fresh lemons imported into the USA from Mexico. And as the amount of lemons imported increases, the U.S. highway fatality rate appears to be decreasing. Okay, it has R squared is called the variability. To find R from R squared, you're going to take the square root of, so the square root of 0.97. Well, that's not the right thing to do. Let me get back to the home screen. The square root of 0.97 tells us that R, and it's 0.98 here. Now look at this. This says it's a positive association. This is definitely negative. So if you are given R squared, which is called the variability, we'll talk about that more later. To find R, you just take the square root of 0.97, which is 0.98. But then you have to look at, is it positive or negative? This is definitely negative. Now you have to think through that on your own. Okay, so there is a definite decrease in highway fatalities as we import more lemons. Now, that's the association. There's a strong linear association here, but does that mean importing more lemons will cause the fatalities on the highway to go down? Not at all. Not at all. Somebody found a whole book last year that had all kinds of silly correlations. I'll have to find a few and post them or show you in class. So another little note down here, it says, hey, there's a strong positive association between monthly ice cream sales at Baskin-Robbins and monthly drowning deaths. Does that mean we should close back at Baskin-Robbins to save people from drowning? I mean, that seems silly. Okay, it just so happens that when people are swimming, it's hot out and people buy more ice cream. So there is an association just because of time of year, but it doesn't mean cause-effect. All right, so there are instructions on your calculator now. So summary, you can never prove cause and effect from a scatter plot. Definitely important. So to make scatter plots, I briefly touched on that. Enter in your data. It gives you a little note on how to sort. Sort list 1, list 2 if you want to keep it paired together. So it'll put list 1 in order from smallest to biggest, but keep the Y values with it. Calculating R, this is very necessary for you to do. You need to turn your calculator on, go to catalog. The catalog is down at the bottom, right at the 0. So catalog is right above this button. So go to second, catalog, and you've got, these are all of the commands you can give it. You're going to go down to diagnostic on, so just hit that down arrow until you get to some D's. Yeah, you'll run through the X's there. They're called chi-squared, so it looks like you're in X's. So I already passed it. I need to look for, oh no I didn't, diagnostic on. I need the DI's. Diagnostic off, no, I want diagnostic on. Now I hit enter to get it on the home screen. Enter again, it tells me it's done. Now when I go to calculate a linear regression, okay, so I'm just going to do both. Now I'm going to stat, calc. Well, first of all, let me back up. First you need to go to stat edit. You need to have some data in a list, two lists, X and Y. So clear, clear. So I'm just going to put some data in a list. I'm going to put the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here, and then I'm going to put 10 numbers here, 52, 53, 56, 59, 57, 59, 60, 63, 59, and 70. Okay, so I just threw some random numbers in there. Now I've got stuff over here in list 3, guess what? Doesn't even matter. I don't even care. So I'm going to go to second stat plot, so I'm following these directions. I'm going to turn my stat plot on. I want the graph type to be the first one, so make sure it's flashing and highlighted. Tell my calculator where my data is, hit graph, and then I want to zoom 9. There's my scatter plot. Look at that one stray little outlier there. If I want the numbers, I can hit trace, then I can sketch it on my, I can get the scale on my paper. I would probably go 1 through 10 here and start with 52 on up here. Alright, so there's my scatter plot. I can tell that this is basically a strong positive linear association with one exception. This point here is very far away in the Y direction, not in the X direction. Okay. Alright, that was the bell. Sorry about that. So now if I want to know what's the linear regression. What is the regression line for this? Okay, so now you have to have your data in. So in order to do a regression line, y equals a plus bx, a linear equation to represent this, in order to do that, you first have to have your data in. So you have to put data in to do this. So now I'm going to go to the second quit. I'm going to go to my home screen. I'm going to go to Stat, Calc. Now I want linear regression A plus BX. You'll see a linear regression here. You never do that one. It's the 8th one, so you hit 8. Okay, it's the 8th one. See, it says right up here I'm doing A plus BX. So tell it where your data's in. Don't put anything in the frequency. Now you can store your regression equation or not. It's easiest to store it right now. You want to store it in Y1. But in order to get Y1 here, so in the Y equals you want to store it, but you don't push that button. You're going to hit the vars, the V-A-R-S, varsity, vars, not varsity, vars means variables, and you want the Y variables, and you want to pick which function you're going to put it in, and you say Y1, and then it tells you Y1. So now what your calculator is going to do is it's going to calculate this equation. It's going to tell you what A is, what B is. It's going to tell you what R is, the correlation coefficient. After you tell it to calculate, and then it's going to put this equation with the A in place of A for the y-intercept, B in place of B for the y-intercept. You also need to be able to recognize the linear regression equation is B sub 0 plus B sub 1x. Okay, these are the y-intercept. These are the slope. Okay, so now I just go down, hit calculate. So now it tells me, okay, there's the form I should write my equation in. There's my A, 556.6 repeating. There's my B, 0.93 repeating. There's my R squared, so I'll write that, which is 0.068. That's probably good. We want to make sure we write that. We will definitely be talking about the variability. And then R, 0.261, okay, or just 0.26. So then I would write my equation, y equals 56.6 repeating plus 0.93 repeating x. There's my linear equation. There's just our general equation. So now what I can do when I graph it, now if you hit the y equals, Notice your calculator put that equation in there. Now it puts a lot of 56.66666. It doesn't round anything. I mean, it rounds it eventually. So that's the best way to do it, is to use that vars, y vars. Now if you hit graph, it'll give you both your scatter plot with your line on it, and then you can sketch that on your paper. So that should be something helpful. You've got quite a few pages to read in 2 different sections, and then you've got some problems to do. Thank you very much.